Good morning. I'm Kelly Herrell. I'm the VP and GM of the Software Networking Business Unit here at Brocade. Good to have you here. We've got a bunch of smart folks from Brocade here in the room, and me. So, you know, I clearly misinterpreted what the field day was about when I started putting the clip art in here, and thankfully somebody did a diving save and put a picture of a data center in there. I'm going to be talking about NFV just to kind of open this up, because the NFV activity and the trending that's going on in here is really, really hot. If you count back, NFV, the three-letter acronym, is about 15 months old. That's it. And it is trending really, really hard because there's a lot of practical applications of it, because a lot of the technology hurdles are much lower than for some of the things in the SDN world. They're very complementary, but they are different. Right now, one of the people we wanted to have talk to you is the CTO of Vyatta, who is also running all the development for Vyatta. But he's in Malaga, Spain right now at the SE NFV working group, which is I think the 6th or 7th one since the instantiation of it. And next week, actually, at Mobile World Congress in Barcelona, there are going to be a number of large-scale NFV announcements coming in from vendors all across the industry. So NFV is coming in like a storm, and I want to kind of put that in context of what's going on and kind of distinguish that from SDN and some of the new challenges that NFV is bringing up and how we're addressing them, and then we'll go from there into deeper tech topics more oriented toward SDN. So first, just the obligatory slide, you know, the reason that we're so interested in NFV is that Brocade has a very significant position in the data center worldwide. When you look at networking between SAN and IP, Brocade's actually got the #2 footprint in the world. The vast majority of that is SAN, but we find that that's a very strong position for us to begin exercising a new vector of attack with IP networking, and software is really leading the charge in that. So the reason that we're very interested in this movement is that the network is changing, as we know, because the compute environment is changing. We don't go around and change networks just because we're interested in changing networks. The drivers for the value are the application. When the application model changes, the network has to change. And from an enterprise perspective, if you think about the network that supported a mainframe model, that was one kind of network for dumb terminals. Then you go to client server, now we need a LAN. Didn't need a LAN before. Then you go to thin client, now we need a WAN. We didn't need a WAN before. So anytime you get to the application cycle changes, or the model changes, it necessarily requires the network to change. And it's the application model that's changed right now that's driving this force is largely virtualization. It's the virtualization density. It's the virtualization velocity. It's the centralization of compute and infrastructure because of cloud. And so we're at this point right now where once again networking is really struggling to change and needs to change because the old legacy models are not working in this new application environment. So we all know that, but this is the thing that's really interesting as it relates to NFV, is that when you look at system architectures, not network topologies, but the actual system architectures, they will decouple over time. When they decouple between hardware and software is up to a number of facets, a number of different elements of technology, a number of different elements of vendor behavior, but they will decouple. And the simplistic view of this is that when you have a monolithic design, it's a black box. Inside of it, it comes with the CPU, with an OS, with some apps. New system designs often begin with this closed monolithic design. But what happens over time and on certain schedules is that once we get to a point of saturation of meeting the requirement and a new need comes in, systems will decouple. The software will separate from the hardware. And this happens regardless of the industry. So this happened in a much bigger industry than networking. It happened in compute. Back in the 90s when the mainframe, which was a black box, gave way to Unix. It was about 1993 when that first really started happening at large scale. And so what you had now is that now you're shipping a Unix box, which yes is, if I'm Sun, it's my processor, and yes, it's my derivative Unix, but now I've got applications on top of that that are coming from an ecosystem above, which starts to blossom. And then ultimately Unix went to Linux, where it's not a SPARC or a RISC processor, but it's actually an Intel processor. The reason Linux took over is because you could do Unix-like processing at 1/10 the cost of of Unix. You could do it with Linux on an x86. So the system decoupling it's a natural trend in system architectures, and what's happening right now in networking is that this is what NFV is. We were going from the device era to an NFV era. If you look at the NFV, all of the NFV demos that are going to be done and shown next week at Mobile World Congress, and there are going to be a lot of them, the vast majority of those are on Intel. The vast majority. You'll see a few that are not, but probably 90-some% of those are going to be on Intel. So this is simply what NFV is about. The fundamental of it is that we're seeing system architectures decoupling, and when that happens, a lot of goodness comes with it. So somebody asked me about the how networking has been working its way into the server, and I finally ended up kind of drawing this very simple picture, which shows, and this is a simplification, but it helps a lot of audiences understand what this change is. You've got network hardware and you've got server hardware. Inside the network hardware, you've got network software. It's working its way into the server, but it's been working its way into the server in a certain path. It all started with virtualization. As soon as you had more than one application in the server, you had a new L2 hop problem, right? The packet comes in, it doesn't know which VM to go to. And that was stage one, right? The vSwitch. We all know and love the vSwitch, right? Love it, hate it, it's there. And it's now pretty much saturated in the industry. Once you got enough virtual machines in the box, we started running into the issue where you need 3 through 7 services to be able to segment or control the traffic between them. And this is when virtual firewall, virtual router, virtual VPN, virtual load balancer, these kind of things started coming into market. And you can actually time it. You can look at the scatter diagram over time as to when vendors brought virtual versions of their hardware-based products into market. And it all happened over the past 3 years. And there was a really dense period where they were all coming into market. Now, as this was going along, we started thinking about the orchestration environment. And it always had been focused on compute and on storage, but now it needs to deal with the networking as well. So this is when OpenStack really started tuning in more to focus on Neutron. Brocade has a blueprint that we've offered into the OpenStack environment called Dynamic Network Resource Manager to be able to utilize more fully the OpenStack environment for provisioning virtual or physical infrastructure. And then the more this complexity came in here, the more we needed to usher in simplicity of management. And this is really kind of the timing of the SDN controller coming into play. We're big believers in open daylight and the progress that is being made there. It will take time, like anything. It will take time for that to mature, but this is the rough timing of that. Now, at some point, you're going to run into this issue of how do I scale all of this server-based networking across a range of servers, and this is what we refer to as NFV infrastructure, as opposed to offering virtual machines as a service inside of that infrastructure, actually having NFV be a distributed form of networking across that infrastructure. So it's been very kind of methodical and on a time basis of how this has been generally working its way into the server, and as a result you see the value transference coming out of the networking hardware and increasingly, but not entirely, into the server. So really constructive impacts for the industry when you have this separation or this deconstruction of systems. One is at each level you get best of breed competition. So if you just think about the hardware pace, how fast does network hardware change in terms of getting better, faster, cheaper? It's measured by years on the upgrade cycles, right? But how fast does the server go? About every 6 months. Okay, now that compounds. It's not just how fast it is, it's the compounding effect of that. That's also true with software releases, how fast you can improve the software release. So when you got the whole stack of hardware, software, all the ecosystem around there, the combined pace of change actually blows past what the monolithic design could do. And you also have the force of all this industry R&D as opposed to the R&D path and roadmap of a single vendor. And the industry R&D is massive. I mean, Intel has twice the R&D of Cisco. They've got over nearly $11 billion of R&D, and it's really focused in one place. And they're running 6 month cycles on their standard stuff. So really strong impacts to the industry. It brings in new opportunities for the way people want to use this stuff. It brings in new competitors, which is good for customers. And then the customers, they benefit from how fast they can do solution design, especially when you think about telcos. Somebody described to me the telco problem of being able to come up with new services and offer them. They called it the problem of the 3 2s. It takes 2 years, $20 million, and it's too late. And that's how long it takes. That's the pressure that the telcos are under, which is that they cannot pop services out really quickly. They can't do it locally, regionally. It's just very, very slow for them. And they're struggling against much more nimble, new age competitors in this space. You can hit really innovative implementation designs because you're no longer constrained by the physicality of the box. You can actually spread infrastructure around much more easily. We have some very interesting POCs with tier 1 service providers on network designs that we didn't even foresee, because somebody realized how many degrees of freedom they had to work with, and they came up with new ideas. And they're strong and they're innovative. You do all this at a much, much lower cost of infrastructure, and it gives you the agility and the efficiency that they're looking for. So when we look at this deconstruction of the networking from a hardware to software, and you look at who's taking the real first advantage of it, the first ones to really pick this up were the cloud service providers. And this does make sense when you think about it. They don't have big far-flung networks. They don't have a whole lot of legacy network that they have to worry about. They're contained within an environment. And really importantly, they have a business model that says that they need to be able to deliver services at utility prices. If they can't deliver services at utility prices, they don't have a business. So they make the most aggressive, the most viciously aggressive technology decisions that they can from a price performance standpoint. And when you look at an enterprise IT, which is ultimately paying these services, an enterprise IT budget is only 100%. Whether it's raising or shrinking, you've only got 100% to go around. And it's increasingly diverging or divesting itself of direct infrastructure purchases of their own and increasingly buying into cloud-based services. And this is going to be a long-term trend. So the new buying force here really is in the cloud service providers as it relates to the enterprise IT budget. And so if you look at today where we are, there's, I don't know, 15% or so of enterprise IT budgets that are being consumed in the public cloud. And this is where we found our first wave of repetitive adoption of Vyatta Virtual Router is in service providers like these, who are all production with services. And what they do is a cloud provider comes in with the most generic network possible. Because if they get their network too specific, it's going to really narrow their addressable market. Right? If they get a network that's really specific for healthcare, then it's not going to work for consumer goods companies. So they come in with the most generic network as possible, and then when customers want to bring their apps and their data into that environment, then the cloud provider offers them an upsell. They'll say, if you need to segment, secure parts of your network, we have an on-demand service. If you want that, just go to our portal, fire it up, and we will automatically deploy these virtual routers, hand you the keys. You can create network segments. You can do firewalling, NATing, VPNing. You can do anything that you need inside of that environment. First example of that was Amazon a couple of years ago. Now Rackspace, SoftLayer, which is the big IBM cloud, and a whole bunch of others are offering this as a paid service. And the interesting thing about the cloud providers is that it's a very perfectly competitive market. Just about everybody can see. It's like the old hosting market. Everybody could see what everybody else is offering and how much they're charging. So it's a race for feature addition, for services addition, and for price competitiveness. So I anticipate that the vast majority of the cloud providers in the world are going to be taking this approach within the next 1 to 2 years, because we're adding a lot of cloud providers to our customer list as it stands right now. So, I refer to that almost as NFV 1.0. It was the simplest thing in the world, right? I don't need a mid-range router. I don't need a mid-range firewall. I can use this virtual machine instead. Now, as that was being proved out, and as the COTS server was getting better and better at packet processing, the telcos had been watching this, and of course Intel had been telling us and telling what was possible. So not last October, but the October before, so less than a year and a half ago, is when the service providers, like the top 15 or so, collectively co-authored this paper, Network Function Virtualization, a Call to Action. And what it was you could see that the network, the service providers were asking their vendors one by one, please change the architecture. This is not working for me. It's too expensive, too unwieldy. It's too slow for me to bring up services. I need things that are based on very commoditized servers with a lot of flexibility of software. This is what I need. And the vendors were not responding very aggressively, because you can imagine what that would look like if you were in the business of selling monolithic designs. So the service providers came together and co-authored a paper. I've never seen it happen before. And co-authored this paper, and it hit the ground just like a bomb went off. And now there are over 30 service providers that are in the NFV ETSI consortium. a lot of vendors. We went to the first Etsy meeting where they're setting kind of some reference designs and working those details out. And at the first meeting, there were fewer than 150 people there, and that's probably tripled by the one that's going on in Malaga right now. So it's really picked up a lot of speed, and this is what they're looking for. They're looking for these benefits. They need to be able to automate. They need to be able to scale services up and down. Over-provisioning, buying a whole bunch of heavy hardware just to cover your peak is a killer. It's an absolute killer. Or having to provision all of this hardware just so that you can grow into it. It's really, really rough on the P&L. And so your only option is to not buy that much, and then scaling up is a stair step and a slow function. So they want as much flexibility as they can get. They want to get as efficient infrastructure as they can get, and that's probably more of an OpEx statement than a CapEx statement.
So how quickly are they going to do that? Like carriers, service providers are all big on talk, all right, and short on action. Right. Right. Yep. So lots of promises and deliver very little.
Yep.
We know that, you know, we all know that DSL took 20 years to get adoption. Right. And they're only just finishing it off now. But we really need to be already into the LTE era. Right. We want Wi-Fi. Right. So why are the services? They do move slow, Greg. I think we need to see within a little over a year, it's gone from a non-concept to a concept where every tier 1 service provider in the world has NFV POCs going on right now. Yeah. So that's a newness, right? Yeah. So then the question is, how quickly are they going to deploy? Well, it depends. You pull a Bill Clinton. It depends on your definition of it. Yeah. You know, what are you trying to deploy? Are you trying to simply take a box out and put a server with a piece of software on it and just say, hey, I got a CapEx reduction right there. I proved my point. That's what some people are going to do right out of the gate because it's lowest risk, fastest impact. There are others just thinking, hey, maybe I should be able to redesign my entire topology and boil the ocean. Well, those things are in the big R&D phase, and that's going to take a long time to roll out. So I think you're going to see the bookends on that, and you're going to see spectrums of implementation models coming out. But I would anticipate that the first rollouts, are in terms of operational rollouts, will be in 2015, right. Based upon what we're seeing. 5 rollouts. With the full ecosystem integrated into the OSS, BSS systems and the whole. Yeah. And you know, whether it's to enable new services or whether it's to tap into the existing infrastructure and just take the cost out, I think both of those things are going to have different levels of drag regarding how compliant you need to be. If you're taking a route reflector out and putting a new one in, the ops guys are going to be all over it before they allow it in. But if you're enabling a new service, I think there's going to be more degrees of freedom that they're going to be allowed to have. Yeah, so you see it rolled out into LTE base stations or things like that rather than... Yeah, exactly. So the one thing that's true about the telcos is that as they move into this world, they're going to be stressing the systems a lot more than a cloud provider does. When a cloud provider stresses a virtual network device, they're doing it from the traffic level of a single tenant, which tends to be relatively small. Right. The telcos, they're going to be putting this to a much bigger test. We'll call it the 10x test here, and they're going to need a lot better performance out of virtual software. So in general, if you look at this kind of layer 3 and up arena, you can see that the kind of the horizons are, you know, if you need a gig of performance for a router or a firewall or what have you, you're going to be in $1,000 for the box. If you need 5 gig or something, you're going to be 10. You end up with this logarithmic pricing model in the monolithic hardware world. So the proprietary hardware cost curve runs like this, and clearly this is what the telcos are asking for, is to bring that down, to flatten that curve out. And this is what we are doing right now. Vyatta is in the 1 to 2 gig space with the current product that we're shipping right now, but we are in the process and are actually in beta right now of our next generation, which multiplies that performance by nearly a factor of 10. And that's what we're going to talk about here for the next few minutes. The reason that we're able to do this is that we all know servers are getting a lot more power, right? A lot more cores, driving a lot more density of the virtual machines. Everybody knows this story. But this is what's been happening as that's been progressing over that same timeline. This is the packet throughput. And I'm talking about small packet IP through a standard off-the-shelf server, HP, Dell, what have you. And this is what you can actually do now if you've modified your software architecture to be able to take advantage of this, because Intel's been doing a lot of stuff under the hood, and just laying down a flat VM as a guest on top of a hypervisor is not going to be able to access all of this power. So I'm going to talk about that. But as this happens, this is also what's driving this change in the throughput of the servers up to the top of rack. So more and more servers are starting to ship with 10 gig NICs instead of 1 gig NICs. Because they're so powerful, they have the packet processing throughput, they're jam full of VMs that are driving traffic. They need bigger pipes out. That's driving, so 1 to 10 off the server is driving 10 to 40 at top of rack, and then it's driving 40 to 100 down. So all of this change is happening because of that density of virtualization, the thing we were talking about before. So where's James around here? Got James Kwan here in product management for Vyatta, and I wanted to talk about the changed architecture between our current product and the one that we're coming out with now.
Okay, thank you, Kelly. So this is a very high-level architecture of the current Vyatta 5400. It has the control plane elements and the data plane elements, but all in sense, it's a single combined control plane data plane product. It runs on Linux, and if I would make a good, a very simple analogy of how it works with a normal 4-core Intel processor, is that when packets go through the system from ingress to egress, each and every one of the modules will make a call to the CPU because, yes, I'm doing source NAT, for instance. Then, yes, I need to go to the CPU, get some processing power, and transfer the packet or NAT the packet. Now, what we see is, in terms of performance of the entire system in total, as we add more cores, we see a linear increase in throughput as we add more cores. Of course, a Vyatta with 1 core will perform slower than a Vyatta with 2 core, 3 core, 4 cores. And what we see is a graph, a throughput graph of something like this. It starts increasing quite linearly as you add more cores. However, once we get to a certain point, is around 8 to 10 cores, depending on the system, we see the throughput not increasing at all. The main reason for that is once we get into that kind of a high throughput, the Linux is doing its best job trying to schedule all these modules. It uses the traditional Linux preemptive call model. However, at very, very high speeds, the bottleneck starts shifting from your processing limitations to your scheduling limitation, where this whole entire system is getting far too many cache misses because I'm not scheduling this correctly because there's too many packets going through at too fast speeds. So once that starts happening, then let's say this QoS goes to core 1, but I got a cache miss. I have to go to my physical memory, which takes a long time. If it's not there, I have to go to my disk, which is kind of like forever. And while it's doing that, it cannot serve that data model process because it's holding that CPU for a cache miss. So that is what we found out as a fundamental limitation of the current architecture that we have. So our next gen, what we changed is we split out the control plane and data plane into 2 separate systems. Obviously, for this product, it will run packaged in 1 VM or 1 bare metal, but the functionality are separated out into a control plane element and a data plane element. Actually, the control plane element, we haven't made any architectural changes. All we did was we upgraded all of our unicast routing protocols to get more scale. However, the data plane was completely re-architected based on C. And the architecture that we chose to use is the well-known packet pipeline architecture. So in this model, what happens is each data plane represents a packet pipeline. And with using Intel's DPDK, Data Path Development Kit, what we were able to do is we were able to kind of core pin every single one of these packet pipelines to an Intel CPU. So hypothetically, in this example, let's say I'm putting 2 cores on the control plane, 2 cores on the data plane. Now I have a system that have a data plane, 2 packet pipelines allocated to 2 cores. And when the packet goes through the system from ingress to egress, now this packet, as it's going through, has 100% dedication of this CPU. It will not be interrupted, and it will fully utilize the L2 and L3 cache of the CPU. And in this case, I have 2 packet pipelines, so I could process packets simultaneously. Now, with this change of architecture, fully utilizing Intel's DPDK, what we're seeing in terms of throughput is dramatically different. This is what we saw with our existing 5400 architecture. And with the 56, we see great differences. First, we were able to go up to around 200 million packets per second on a 2 8-core system, so 16 cores total. At that point, what happened was we ran out of PCI bus, but we were able to hit that 200 million packets per second, which kind of equates to around what, if we measure on a per core basis on a bare metal, we're getting around 14.5 million packets per second on a per core basis. 14.5 million packets per second is approximately 10 gig line rate. So hypothetically, on this Dell server, which we're testing on, we allocate 2 cores on the control plane, 14 cores on the data plane. We are kind of theoretically getting around 14 by 10 gig throughput. Of course, this is a lab environment, but that's kind of what we're seeing, right? So
I'm curious, did you capture any performance numbers? Like you got the performance for the packets per second. I'm curious, the impact to the CPU, because if this is hosted with VMs, do you have any numbers on that? I'd be interested in seeing it.
So the question was, when we measured this at a certain speed, did we have any CPU utilization captures? So one thing is, when we reached around 85 million packets per second, we were hitting around roughly 35% CPU utilization across. Right. So at 200, I forgot the number, but we ran out of PCI bus before we ran out of CPU.
So it's
CPU
like 30, 35 max?
Yeah.
Okay.
Now, with this product, we have, we have a few use cases. One, ironically, is the telco use case using virtual route reflector, right? I'm saying ironic because route reflectors are a typical thing that doesn't really forward data. This was very interesting for us because this was one of the first NFV use case that were coming out of our carriers. And they were very smart about this because they had the doubts of doing NFV on a COTS server, going from a proprietary custom built to a COTS model. So they wanted to be careful. They wanted to use something that really did not hit the data plane aspect. So very, very interesting. And the scale benefits that we got, all the unicast, I mentioned about us upgrading all of our unicast routing protocols. And one of the reasons was that we wanted to cater to this type of a control plane only use case as well, where the incumbent hardware in terms of number of routes on a route reflector was doing around 550K routes. With our 5400, we were able to do around close to 3 million routes. We were able to do this because memory on a custom-built router is very, very expensive and has an upper limit compared to a x86 server, right? We have kind of a literally infinite amount of RAM in that sense. 128 gigs, no problem, right? And with the upgraded unicast routing protocols using advanced multi-threading and all this other architectural benefits, we're kind of able to hit approximately 13.5 million packets on the upcoming 5600.
Wow, that's a significant advantage.
Yes, it is a significant advantage. Of course, some might argue, hey, who needs 13 million routes on a route reflector?
IPv6.
Yes, exactly.
Yeah.
And then to sum up other use cases across the board is, yes, we have 2 sectors of use cases, one on the service providers, another on the enterprise. On the service provider side, it's heavily focused on NFV use cases of virtual route reflector that I just talked about. Others are all VPC use cases within our cloud environment. You can see us being deployed in Amazon, Rackspace, et cetera, et cetera. Once we fall over to the enterprise side, the use cases change to more of a virtual CPE type, or a method of connecting your private cloud to your public cloud. That is one of the other widely used use cases where you have a virtual router, Vyatta virtual router, in places like Amazon, and you have another one in data centers like us, and you use those two to do L2 VPN bridging between the 2 data centers, so they will look kind of flat, right? Also, other use cases include, with the high performance of 5600 is our use cases that are kind of coupled with specific hardware products. Like one good example is a Metro E, a packet optical switch coupled with the 5600 that could have multiple 10 gigs on a server. You couple those two, then those are a very, very attractive data center to data center connectivity solutions that is very flexible and a very low cost.
So the nice thing about this, and the reason that we wanted to talk about this, is as I said, the NFV movement. Thanks, James. The NFV movement is really powerful for a number of reasons. One, the interest is really high, but some of the hurdles to actually getting to the first deployments are actually relatively low, and a lot of the proof points have already been made in the cloud service providers for tenant routing and those kinds of functions. So we're just seeing this pick up speed. Again, I'm not quite sure. We'd have to find what some comparable metric is, but the NFV movement is at least as explosive as the SDN movement in terms of interest. But I think it's even faster to realization in terms of production in some of these.